Good morning, students. Yesterday we have learned two types of friction, static friction and kinetic friction. Okay. Now we will define what is friction in general, whether it is static friction or kinetic friction. Friction is the horizontal component or parallel component of contact force which opposes the impending motion or actual relative motion between the two surfaces in contact. So let me define the general meaning of friction. So friction in general is the parallel component of contact force which opposes the impending motion when the body is at rest. Which opposes the impending motion when the body is at rest or actual relative motion when the body is in actual motion. Actual relative motion of the two surfaces in contact. So this is how we conclude what is friction. It is a parallel component of contact force which opposes impending motion when the body is still at rest or actual relative motion between the two surfaces in contact when the body is in motion. Okay, let us consider one situation. Think that there is a box. Think that there is a box kept on the surface of a railway compartment. Suppose this is a box kept in a railway compartment on the floor, and the railway is the train. It is kept on the train in the compartment. It is kept in the compartment of a train, and the train is accelerating. Think that this box, like your suitcase or trunk, is at rest, and trunk is at rest, and the train is undergoing acceleration. What does it mean? The trunk is also accelerating in the same value as that of the train. The trunk is also accelerating as the same value as that of the acceleration of the train. I think you got the situation. Consider the box kept on the floor inside compartment of a train, and the train is accelerating and the box is at rest. Right? When the box is at rest, it means the box is also moving with the same acceleration as that of the acceleration of the train. What makes this box to be at rest with respect to the train, moving train? So definitely there must be some force acting on this box to keep it at rest. What are the forces? One is the weight of the box, which is acting vertically downwards, which is exactly balanced by normal reaction even when the train is at rest. Okay, when the train is in motion, suppose this is the direction in which the train is in motion and the box is also moving with respect to train with the same acceleration. There must be some horizontal opposing force. This horizontal opposing force opposes the impending relative motion between the two surfaces in contact. Suppose, for example, if there is no friction between the floor surface and the box surface, then the floor would slip by. The floor would slip by and the box would have moved back. Slowly it would have moved back and hit the wall of the compartment. I think we got the situation. Suppose this floor is very smooth and floor is frictionless. If it doesn't provide any friction, when the train starts moving in this direction with some acceleration, then if there is no friction, the box would continue to move backward because box tend to be at rest. When the box tend to be at rest, the floor is moving with acceleration. So as a result, the box would slip by and the box continue to move backward and go, and it will attach with the wall of the compartment and stop. So if it is at rest, it means what? There must be some contact force. That contact force must be in the opposite direction. That must be static friction. The impending motion is opposed. Impending motion is opposed by this friction, and this friction is a static friction. Then how much should be this maximum value of static friction so that the box will be at rest? So if you calculate that, it's going to be very interesting. If m is mass of the box, then if you draw the weight of the box, weight is equal to m into g, and the normal reaction is exactly equal to this weight in the upward direction. So that becomes normal force exerted by the floor. So n is also equal to mg. If a is the acceleration of the train, a is the acceleration of the train, then the opposing force Fs max should also be providing same acceleration in the opposite direction, so that net acceleration of the box becomes 0 and the box will be at rest. So that is how we are going to calculate. So here, if ma is the force, applied force, you can say ma is the applied force due to the motion of train, where m is the mass of the box and a is the acceleration of the train. So force acting on the box would be ma. So this ma should be balanced by, see, this ma would be in this direction. If this is the applied force in this direction, F is equal to ma. This should be exactly opposed by Fs, right? And this Fs should be less than ma. Then only box will be at rest. If Fs becomes Fs max, then what happens? Then the box will tend to move. I think you got it. So if ma is the force applied on the motion of the train, then this ma should be equal to Fs, static friction. What is Fs? Static friction. What we have learned yesterday, where Fs is less than or equal to mus n. For any value of static friction, it is always less than maximum value of static friction, limiting value of static friction. Then only box would be at rest. The box doesn't move at all. If the applied force becomes exactly equal to Fs max and greater than that, then the box tend to move. Okay. So then what is n? Here n is also equal to mg. Therefore, Fs must be less than or equal to mus mg. So if you substitute this Fs equal to mus mg, then ma is equal to mus mg. Ma is equal to mus mg. But this is less than mus. Ma is equal to Fs, but Fs is less than or equal to mus mg. Therefore, ma is equal to mus mg. When Fs becomes Fs max, when applied force is equal to Fs max, static friction becomes Fs max. Then what happens? Fs max is equal to exactly according to law of static friction. First law of static friction, yesterday you have learned. Fs max is equal to mus n. Then this acceleration will be taking maximum value. For all other acceleration values MA, it will be less than mu s mg. When the Fs becomes Fs max, A becomes A max. So I write here, when Fs becomes Fs max, acceleration A becomes A max. So now I can substitute here Ma max. So therefore Ma max is equal to, right, mu s n. Now substitute the value of n. What is the value of n? N is mg. N is mg. So m cancels, therefore A max of the train is equal to mu s g. So with the help of coefficient of static friction of the floor, coefficient of static friction exerted by the floor surface with respect to the bottom surface of the box, if it is a mu s, so we can find out what is that maximum acceleration of the train beyond which the box tend to move. Okay, below which the box is still at rest. The box is still at rest. This is the maximum value of the train. I think you got this. Based on this, we are going to solve one numerical problem. Okay. Okay, look at this problem. Determine the maximum acceleration of the train. Maximum acceleration of the train in which box lying on its floor remains stationary, given the coefficient of static friction between the box and the train's floor is 0.15. So the coefficient of static friction between the box surface and the train's floor is 0.15. It is given. And what should be the maximum acceleration of the train in which the box lying on the floor remains stationary? So just now we concluded, for the box to be remaining stationary on the floor of the train, the force exerted by the pull of the train must be equal to the maximum value of static friction. Maximum value of static friction. Beyond that, box starts moving. Beyond that value, the box starts moving. Below that, box will be still at rest. So the condition is that force of pull of the train must be equal to limiting value of static friction. Force of train must be equal to limiting value of static friction. So if m is the mass of the box, same diagram we can refer. If m is the mass of the box and A max is the maximum value of acceleration of the train, A max is the maximum value of acceleration of the train beyond which the box starts moving, below which box will be still at rest. Below which box will be still at rest. Ma max must be equal to limiting value of static friction, Fs max. And what is Fs max? Fs max is equal to mu s n, where n is equal to mg. Therefore, Ma max becomes equal to mu s mg. So here it is given in the problem. Take g equal to 10 meter per second square for simple calculation. So 10 g equal to 10 meter per second square. So m cancels. Therefore, A max, maximum acceleration of the train which tends the box to be still remaining at rest, is equal to mu s mg. So mu s doesn't cancel here, m cancels. Okay, so m cancels, so you are left with mu s g. See here, you can see 0.15 into 10. So it becomes 1.5 meter per second square. This is very interesting. So for the box to be at rest, the maximum acceleration does not depend on the mass of the box. It depends only on the coefficient of static friction. Depends only on coefficient of static friction. 0.15 into 10 becomes 1.5 meter per second square. This is how we need to solve the problems from this consideration. Now let us see another interesting situation. Now the box is on horizontal floor. If it is kept on an inclined plane, what happens? Let us see that. Okay, let us now learn one more interesting angle. It is called as angle of repose. Consider a box being kept on a plane. Box of mass being kept on a plane. Let the mass of this box be m. Then we know that if this is the center of mass, we take this as a reference point. Then if this is the weight is equal to mg, right? Then this weight is balanced by normal reaction, normal force exerted by the plane, and thus it is at rest. And we know then if you apply any external force, then there will be a force of friction, static friction, if the body is still at rest. So the force of friction exerted by the body, still when it is at rest, we simply call it as static friction. Now suppose this plane is slightly inclined. If this plane is slightly inclined, suppose the same plane is now slightly inclined like this, with certain angle with respect to the horizontal. Suppose this is a HO and this is A and this is B, right? Same box is now in this position. Same box of mass M is now in this position. Now this angle theta is of our interest. As you go on slowly increasing the height, as you go on slowly increasing the angle of inclination, suddenly the box doesn't start sliding down. At one particular angle, what happens? The box starts sliding down. What is that angle for which the box starts sliding down on its own? Below that angle, the box is still at rest. That angle of the plane with the horizontal is called as angle of repose. Angle of repose. So we will find out the angle of repose. Before that, we first write out what is angle of repose. The angle of the inclined plane, the minimum angle of the inclined plane, you can say the minimum angle of the inclined plane, for which the box starts sliding on its own due to its own weight along the inclined plane, is called as the angle of repose. So angle of repose is the minimum angle subtended by it is angle of inclination. You can say it is the angle of inclination subtended by the inclined plane. It is the minimum angle subtended by the inclined plane, for which the body just starts sliding down. It means for an angle less than this theta, the body will be still at rest. For an angle less than this angle of repose, the mass or the block will be still at rest. What is that minimum angle? With respect to horizontal, for which the box starts sliding, that angle is called as angle of repose. So now let us calculate this angle of repose with this situation. Suppose theta is the angle of repose. So we denote it as theta, angle of repose. So what are the forces acting on this body? Now I am considering this as the point of reference for drawing the forces. To show the forces acting on the body, we take one point, usually it is called as center of mass, where the entire mass of the body is assumed to be concentrated. That point we take it as center of mass. With respect to this center of mass, we draw the forces. So with respect to this center of mass, the weight is acting vertically downwards, which is W is equal to mg. Same, W is equal to mg. And you see the normal now. Normal is the normal force with respect to the inclined plane. Normal reaction is the force perpendicular to the plane which holds this block. Perpendicular to the plane is, now you see, this is the perpendicular force. Perpendicular force. Now, what would be the direction of its sliding motion? So this would be this direction of sliding motion. And what would be the direction of friction? Think that it is just still at rest. Then the direction of static friction will be along this surface like this, in the upward direction. It should be in the upward direction like this. So this I am drawing with respect to center of mass. So this becomes Fs. This becomes Fs. Still at rest. For an angle just greater than that, the block just starts sliding. That is the angle of repose. Now how to calculate this angle of repose? Now extend this. Extend this. Yes. You will get component of the forces. Now if this is the angle theta, then we can prove geometrically that this angle is also theta. This angle is also theta. For example, if it is on the plane, the angle theta is 0 now. If the plane is turned by say 30 degree, is it not the block is also turned by 30 degree? I think you got the point. If suppose I am keeping this. Yes, I am keeping this. This is horizontal. You can see this is the plane which is horizontal. Now I am just turning it by some angle. Is it not the block also turned by same 30 degree? It is the normal which turns here. If this is the normal, that is when it is horizontal. When you turn it by 60 degree, normal also turn by 60 degree. If you turn it by any other angle theta, normal also turn by same angle theta. So what is that angle for which you see, you can now see the duster starts sliding. Below that the duster is still at rest. Below that the duster is still at rest. When I go on turning it, still the duster is at rest. Still the duster is at rest. Still the duster is at rest. When the force becomes equal to limiting value of static friction. The static friction is in this direction now. The block tends to move in this direction. So the force of friction which opposes the impending motion is going to be in this direction, is called as static friction. So when you can see now, yes, still, yes, now it is sliding. Yes, at this angle it is sliding, means this force which is tending to move the body must be equal to limiting value of static friction. This Fs must be Fs max, then the body just starts sliding down. So if this is the angle theta, I think you got this angle is also going to be theta geometrically. So the normal also turns by same angle theta. So I can draw the components of this weight now. Components of weight now become mg cos theta along this line and mg sin theta along this line. Mg sin theta along this line. If mg sin theta is just greater than Fs max, then the block starts sliding. I think you got the point. So now in this case, now you can write the forces acting on the block. Forces acting on the block when it is in equilibrium. See here, one flare of force you can see the normal reaction is balanced by mg cos theta. So I write mg cos theta is equal to normal reaction force. Second one is mg sin theta must be balanced by Fs max. Fs max. So that I can find out the value of this theta, angle of repose. Just when this angle is little greater than theta max or this minimum angle theta, then what happens? The block starts sliding. So the question is to find out this angle of repose. Now take the ratio. Dividing equation 1 by equation 2, we get, okay, dividing equation 2 by equation 1. Dividing equation 2 by equation 1. So mg sin theta by mg cos theta is equal to Fs max. Fs max is equal to what? Mu s n. Mu s n divided by n. So on the right hand side n cancels. On the left hand side mg cancels. Therefore sin theta by cos theta becomes tan theta. Tan theta is equal to mu s. Very simple. Tan theta is equal to mu s. Therefore theta, angle of repose, becomes equal to tan inverse of mu s. Very interesting result. The angle of repose is that angle of inclination of the plane for which the body just starts sliding, below which the body still is at rest. That angle of repose depends only on the coefficient of static friction. It depends only on the coefficient of static friction exerted between the floor surface, the surface of the plane with respect to the surface of the block. It does not depend on the weight at all. It does not depend on the weight. That is interesting. Therefore, the angle of repose is independent of mass of the body. Mass of the body. This is very interesting conclusion. So based on this, we can solve one problem. I think you got the point. What is the meaning of angle of repose? So angle of repose is that angle of inclination of the plane beyond which the body just starts sliding, below which body is still at rest. At that value also body is still at rest, just starts sliding. Okay, now let us solve one problem based on this. Okay, see now, based on this, a mass 4 kg, a mass of 4 kg rests on a horizontal plane. It rests on a horizontal plane. The plane is gradually inclined until at an angle of 15 degree. Until at an angle of theta equal to 15 degree with the horizontal, the mass just starts to slide down. The mass just starts to slide down. The mass of this body is 4 kg. What is the coefficient of static friction between the block and surface? I think directly you can get to know. Tan theta equal to mu s. So if you do not understand tan theta equal to mu s, then you need to derive this. So the Fs max must be equal to mg sin theta. Fs max equal to mg sin theta, that is Fs max is mu s n, and mg cos theta, you see when you resolve the components, then if this same angle theta, then it becomes mg cos theta. Mg cos theta balances normal reaction. Mg cos theta equal to n. So when you take the ratio sin theta by cos theta, it becomes equal to mu s n by n. So n cancels, so mu s. Therefore tan theta, here theta is given, tan theta equal to mu s. Therefore mu s is equal to tan inverse of theta. So theta value is given here 15 degree. So if you just substitute the value of theta, tan inverse of 15 degree. So this gives us the value of the mu s. Tan inverse of 15, if you calculate, it comes out to be 0.27. 0.27. This you can refer the table. So it becomes 0.27. So coefficient of static friction becomes 0.27, which is dimensionless. It doesn't have any unit because mu s you are obtaining as Fs by n, right? So there will be no unit for mu s. So just with the help of the angle of repose, we can get the mu s value. So angle of repose just depends on mu s value. More the mu s value, more is the angle. Less the mu s value, less is the angle of repose. In the same way, there is one more angle. It is called as angle of friction. Angle of friction and angle of repose. Both are going to be equal. Let us see how is that angle of friction is equal to angle of repose. Angle of friction. Look here. Quickly we will discuss what is angle of friction. Angle of friction is the angle made by resultant of the force of static friction and the normal reaction with the direction of normal reaction force. Look here. It is the angle subtended between the resultant of force of static friction and normal reaction with the normal reaction. So I will write the definition. The angle between the resultant of limiting value of static friction resultant of limiting value of static friction. What is that limiting value of static friction? Fs max and normal force. What is that normal force? N with, this is the resultant, Cb is the resultant, with the normal force. With the normal force. So refer this diagram. Suppose we are applying a force on this block. We will consider this later. We are applying force on this block so that the block is still at rest. At one high value of applied force, the block just starts sliding. That applied force must be greater than or equal to Fs max, limiting value of static friction. So limiting value of static friction is in the opposite direction. This is the value of Fs max. I have shown with respect to a reference point C here. Actually it is acting between the surfaces which are in contact. Fs max. So this is Fs max and this is the normal reaction. Okay. The resultant of Fs max and normal reaction is this Cb. Using vector diagram I have found out resultant of Fs max vector and normal force vector. Cb becomes the resultant. What is this angle subtended between the resultant with the normal force is called as angle of friction. It is called as angle of friction. This is denoted by alpha. Now look at this diagram. From this diagram I can write what is tan alpha. Tan alpha is equal to opposite divided by adjacent. Opposite is what? NB. NB divided by the adjacent. Adjacent is CL. Adjacent is CL. What is NB from the diagram? NB is equivalent to CA. NB is equivalent to CA. CA divided by CN. What is CN from the diagram? CN from the diagram I can write it here in the next step as the normal force. Therefore, tan alpha becomes CA Fs max divided by CN. CN is the normal force. So mu s n divided by n. So n cancels. So we are getting again tan alpha is equal to mu s. So tan alpha is equal to mu s. When it is sliding, you see, again if you draw the vector diagram and draw the resultant is going to be in this direction. So the angle made by the resultant with the normal reaction and the Fs max is okay. The resultant is this one. This resultant, what angle it makes with the normal, that becomes the angle of friction. Is it not this angle of friction is same as the angle of repose? So we also got angle of repose. Tan theta equal to mu s. So from this tan theta equal to mu s, tan alpha is also equal to mu s. Tan alpha is also equal to mu s. Therefore, tan of angle of repose is equal to tan of angle of friction. Tan of angle of friction. Therefore, this implies angle of repose is equal to angle of friction. Angle of repose is equal to angle of friction. Based on this, you are going to have some numerical problems where this discussion will be helpful. That we will see in the next session and we will discuss the rolling friction. Thank you. Have a nice day.